Hello everyone, this is Mike Dowding with the SD9's Physics Department, and we're going to try and finish up Chapter 9 today. And this last video is going to cover collisions, and we're going to see how things like conservation of momentum and conservation of energy can be combined into these example problems. And we've already seen a couple of examples in the previous video where we had some billiard balls that would collide. So if we had mass 1 and mass 2 collide, after the collision, mass 1 and mass 2 would then have some final velocities that were associated with them. And we said that these final velocities would be determined by the type of collision that we had in our system. And so if we go with the previous examples that we had for the billiard balls, I believe the mass 1 was the cue ball, and that was 0.17 kilograms. Mass 2 was one of the other balls on the table. Could be the 8 ball or one of the stripes. But before and after this collision, we would have to conserve the momentum of the system. And so we would write out the momentum for the cue ball and the 8 ball before the collision, and numerically that would have to equal the final combination, whatever that happened to be. And that conservation of energy could then tell us how fast mass 1 or mass 2 would travel after the collision. That's assuming that both of them do travel. It's possible that one of them could come to a halt, and we covered those situations in the last video. But now we also want to consider, what about conservation of energy? And if we do in fact have everything happening in a one-dimensional system, in other words, the billiard balls remain on the table, and so none of them change their gravity potential, then the only energies in the system that we have that we can track would be the kinetic energies of each mass. So before the collision, mass 1 would have some kinetic energy based on its mass and initial velocity. Mass 2 would have a kinetic energy based on its combination. And then after the collision, we would have the kinetic energies of mass 1 and mass 2 based on their final velocities. But the question here is, does this in fact produce an equality? Because one of the things that we found in our discussions with energy is that it's not always just a matter of keeping track of kinetic and potential energies. Sometimes, in fact, most times, there is some thermal energy generated due to things like friction or air resistance, or maybe during a collision. And in fact, that's going to be very common. We will have thermal energy created during a collision, and so we cannot say that this expression is equal unless we incorporate any thermal energy that was generated during the collision process. And as far as trying to figure out how much thermal energy is generated when the cue ball strikes the 8 ball, we really don't have a method available to us. It's not like we can apply a force to a displacement during the collision, because we're assuming that collision is almost instantaneous, and we don't want anything to move during that instant in time. So the transfer of energy, or the transfer of energy to thermal energy, is not something that we can readily figure out just yet. Now, we did say that the potential energy in this system was going to be 0, because all of the billiard balls are going to stay on the table, and that's where I'm going to assign the 0 point for the potential energy. So we can let the potential energies be 0, and then, well, we can take the difference in the kinetic energies, and that should tell us how much thermal energy is generated. But before we can do that, we would have to know what is the kinetic energy of the system before the collision, and what is the kinetic energy after the collision. And, well, we've got that right up here. The difference in these terms will be the thermal energy that is generated in the system. But that sounds easier than what it is, because right now the only thing that I know is the initial velocities of mass 1 and mass 2. So I know what the initial kinetic energy of the system is, but I don't know anything about the velocities of the masses after the collision. So I don't know anything about these two terms yet. I do know what the masses are, but I kind of need to know what the final velocities of each mass are going to be, so that I can take this difference and see how much energy was lost due to the generation of heat. Well, the way that we would do that is we would combine everything that we had in this equation and pair it up against the conservation of momentum, because momentum is not energy, and the conservation of momentum is going to be upheld regardless of whether we generate heat or not during this collision. So at this point we want to define the two different types of collision that we can have in a system. So 2 types of collisions. The first type is what we're going to call an elastic collision. And an elastic collision is a collision where mechanical energy is conserved. So in other words, the combination of kinetic and potential energy that we have in the system before the collision has to equal the combination of kinetic and potential energy after the collision. In other words, there is no change in thermal energy for the system during this collision. And quite frankly, this is not a realistic case scenario. Any kind of collision that you have out in the real world is going to have some amount of energy lost due to heat generation. And so that brings us to the second type of collision, which is an inelastic collision. And this pretty much follows the same verbiage as the elastic collision, except that this is one where the mechanical energy is not conserved. So in this case, our initial mechanical energy and our final mechanical energy are not equal to one another. And this is more realistic. So this is a real world case. This is what we would call an ideal situation. So what good does it do us to have these two definitions? Up here, in the ideal case, we have a situation that is basically not going to ever occur in the real world, yet it provides us with an equation or an equality that we can set up and then use algebra to rearrange things and solve. The inelastic collision is a real-world scenario, but it provides us with an inequality. And an inequality, that's an expression, but algebraically there's not really anything that we can do with that. All I can say at this point is that the left-hand side is not the same as the right-hand side. But the difference in these values, over here we have a final mechanical energy. Over here we have an initial mechanical energy. What we can do is we can take the difference in the mechanical energies before and after the collision, and at the very least we can say that's not zero. In fact, this difference between initial and final mechanical energies would have to be equal to the amount of energy that is lost due to the generation of heat. So what this pair of expressions down here, go away, there we go. So what this pair of definitions is telling us is that we now have a way of testing to see if a given collision is in fact elastic or inelastic. And like we said, anything in the real world is most likely going to be an inelastic collision. There's going to be some loss of mechanical energy. But that is now something that we can compare. If I have information about the initial kinetic and potential energies, I can compare that to the final combination, and if they're different, then we know that there has been some energy loss due to heat. Whereas up here, in the ideal situation, this is probably never going to happen in the real world. So again, I would ask, what good is it? Well, maybe we could use it as a form of estimation. If there's going to be a situation where we have one object that interacts with another object, what if this collision between the two is a very gentle collision? In other words, what if the amount of thermal energy that is produced is relatively insignificant. In that case, can we estimate the thermal energy to be close to zero and then use the elastic collision case as a way to help solve values for what's going to happen after the collision. So, but before we have initial velocity values for our two masses, and after we would have some values. So can we use this equation as an estimate of the system? And the answer is sure. Why not? The only thing that you have to do is you need to figure out what amount of thermal energy would be considered insignificant for loss, and that might be something that you would have to check with your manager or project supervisor just to see what would be acceptable in whatever line of work you happen to be using this in. So those are the two types of collisions, elastic and inelastic. And now we're going to go ahead and jump into a couple of example problems. So we are going to jump in our time machine and go back about 150 years to the time before computers and lasers and all that stuff. And you're going to take a job as an ammunitions manufacturer. And it's going to be your job to measure the speed of a bullet when it comes out of the muzzle of the rifle. And you need to do this, first of all, in a safe manner, which means staying as far away from all of this stuff as possible. But you still need a means of being able to accurately measure what is going on in the system. So we're going to try a combination of our conservation of momentum and conservation of energy. We want to see when and where these two conservation ideas work best. So we'll jot these down here. And we are going to use the updated version of conservation of energy, because when you're firing a firearm, whatever that bullet strikes is probably going to generate quite a bit of heat. So we're not going to be able to assume that this is an elastic collision. In fact, it is most definitely going to be an inelastic collision. All right, and we'll actually be able to prove that here as we go through the problem, because we are going to find that the initial and final mechanical energies are in fact not equal to one another. All right, so you fire this bullet, but then what? How are we going to measure the velocity of this bullet? It's going to be traveling way too fast for us to measure it by hand. You're not going to be able to see it with the naked eye. So we need to make ourselves some kind of a target that can catch the bullet. And I'm going to bring my work a little bit further down here. So we have some unknown velocity for the bullet, but we're making these bullets. So one thing that we can control is how much mass that bullet is going to have. And I am not an expert in this field, so I'm going to Google the average size of a bullet. mass of bullet. And I'm getting a value that is between 0.02 and 0.04 kilograms. So I will take the middle value, we'll say 0.03 kilograms. So this would be about 30 grams. And that bullet is going to be fired. Now again, we said we wanted to be safe with everything, so we don't just want to fire this bullet out into the open. So we're going to either make ourselves some kind of controlled system, environment, lab, could even be a barn. And what we're going to do is we are going to hang a block of wood from the ceiling. You could just as easily go out and cut down a tree and then hang a log segment from the ceiling. And this log segment, we can also control what the mass of that log segment is going to be. So maybe this is 5 kilograms. And we hang that log segment from the ceiling. So what I have here are 2 strings, and when we fire the bullet is going to enter the log segment until it eventually becomes lodged within the log itself. We don't want the bullet to go all the way through. And what we're trying to do here is we're trying to get all of the momentum of the bullet to be absorbed by that log. So right in here there is a collision between the bullet and the log. And so when it comes to collisions, which of the 2 conservation methods are going to be best suited for us? Conservation of linear momentum or conservation of energy? And well, if we're not sure, let's just see what our options are. We know that when the bullet is fired, the initial momentum of the bullet is pointing to the right, same direction as what the velocity is pointing. And then after the collision, all of the momentum of the bullet will be absorbed by the block, and this block is going to start moving. And once that block starts moving, well, it's anchored to the ceiling, so the motion of that block is going to be restricted to some kind of a circular path or an arc. And that block is only going to be able to swing so high. Oops. Try that again. Before its kinetic energy becomes converted to potential energy. So there's going to be a change in height for that log as it swings up. So right here, right after the collision, the log has some velocity which will carry it through the swing, converting any kinetic energy here to potential energy up here. So it looks like during the swinging of this log, our best bet would probably be to use conservation of energy. We're going to assume that there is negligible heat generation due to air resistance. But the reason why we don't want to use conservation of momentum during this swing is because momentum is a vector. And our conservation of momentum says we have to conserve what's happening in all directions. Well, as this block swings, we're constantly changing the direction of our velocity, and I don't think we want to have to deal with constantly changing direction relating to momentum. Plus, the log itself is not the only thing that's going to be experiencing a change in momentum. We also have these, oh, really didn't want to do that. We also have these anchor points up here that are going to experience some tugging from the swing of the log. So if I can get away with using conservation of energy during the swing, I can definitely compare the energies at the point just after the bullet becomes lodged in the log versus the point where the log reaches its maximum height. And I don't have to worry about any thermal energy being generated here, because the only thing that we're doing is swinging through the air. And we said we're going to let air resistance be negligible. However, during the actual collision, that's where we expect a whole lot of heat generation to occur as this bullet is digging its way through the log. So there's definitely going to be a lot of heat generation during that collision. And I don't really know how I would figure out the work that's done by the bullet in producing that heat. So in this case, the conservation of energy may not be my best approach. However, the conservation of momentum before and after the collision, all my vectors are pointing in the same direction, and conservation of momentum doesn't care about energy lost due to heat. And so during this collision, my best bet would be to use the conservation of momentum. So let's summarize. When it comes to collisions, what's good to use during collisions and what's bad to use during collisions? Well, conservation of, I'm just going to do conservation of momentum is good to use during collisions because conservation of momentum doesn't require us to keep track of any energy that's lost due to heat. As long as our collision remains in a linear fashion, which we have here, we have our initial and final velocities before and after the collision both heading towards the right, then we can do conservation of momentum before and after a collision. But conservation of energy is bad because we don't really have the math necessary to keep track of all the different forms of energy, and it's probably not going to be just heat. If you think about collisions, we already have kinetic energy, potential energy, and heat energy. But are there other types of energy? Are there other forms of energy that could occur in a given system? And typically, you know a collision has occurred because you can hear it. And so there would be some change in energy related to sound. So there could be a transmission of vibrational energy through the air that carries sound. There could be light that is generated. For instance, like a car crash, there could be some sparks, or even, you might have some of your potential energy in the form of fuel catch fire, and then that starts giving off light. And so it starts to become more and more complex to keep track of all the different kinds of energy in a system. And what we're going to add to this list in Chapter 10 is energy associated with rotation. So you're going to have things that are spinning. And that's actually going to be paired back up with kinetic energy, because rotation is still a form of motion. Thus, if we have something that's rotating, it will have a specific type of kinetic energy. Well, what about 2D or 3D displacement? Specifically in the case of our, and this actually has a name, it's called a Ballistics Pendulum. So the log is acting as a pendulum. We fire the bullet into it and it swings. So we are displacing two-dimensionally as we swing, and in that case it's going to be very difficult to keep track of the momentum in the system, and so trying to conserve momentum during that 2D or 3D displacement is not going to be a very good idea. However, during that displacement there's no heat being generated, and so conservation of energy would be a much better idea. All right, well, let's clean up some of what we have here. Need to get my eraser function. I'll clean up a bit of this. And I'm going to mark a couple of spots on our diagram here. I'm going to call this spot, this is location 1. The second spot, or I guess I should explain what location 1 is. This is going to be the system before the bullet collides with the log. Then location 2 is the system immediately after the bullet has collided with the log and it has become embedded, and the log is just getting ready to start moving through its swing. And then up here at location 3, this will be the system when the pendulum reaches its maximum height of h. So we've got three different, I guess you could say, locations or times during the motion of objects within this system. But as we go from 1 to 2, we said that conservation of momentum would be our best bet. And then as we go from point 2 to point 3, conservation of energy would be our best bet. And we already said that moving from point 2 to point 3, we're going to have a negligible loss of energy due to heat, so I'm not going to include a delta theta The only place where we actually have heat generated is between points 1 and 2, but that's not being considered in the conservation of momentum expression. So now we need to fill in all of these values. At point 1, we need to know what is the momentum of the system before the collision. Well, before the collision, the only thing that was in motion was the bullet. The block, if we absolutely had to, we could label an initial velocity for the block, but it's 0. So our initial momentum for the entire system is just the momentum of the bullet, and that is technically to the right. So if we need to, I can plug in an x-axis here. Then we need the momentum just after the collision. So that is at site 2. Now, this is kind of important. When the bullet becomes embedded in the log, it is the combined mass of the two that gets carried off by this new velocity. And we don't know what that velocity is. We just know that there's some velocity that the log is going to start swinging with. And so this is our conservation of momentum equation that takes us from point 1 to point 2. Now we need to figure out, going from point 2 to point 3, how do we conserve the energy? We know that when we reach the maximum height, the final velocity should be 0, and that's the whole point behind being at a max height. So our final kinetic energy should be 0. The initial kinetic energy will be the combined mass of the bullet and the block, traveling with that velocity that the I think I called it a block, it should be a log, but same difference at this point. But we have the big block here that's going to be traveling at that unknown velocity VB after the collision, plus whatever the initial potential energy of the system is, and that's all going to have to equal the final potential energy. So now comes the point where we have to figure out where do we want the 0 point for potential energy to be. And I'm kind of a creature of habit. I prefer using the lowest point in the system, and that means we can allow the initial gravitational potential to be 0, and the final potential will then be based on the final height of h. So that becomes combined mass of bullet and block times g times h, because gravity potential is measured as mgh. A little bit of cleanup here. 1/2 little m plus big M VB squared equals little m plus big M GH. Alright, so we've got our two equations. We have our conservation of energy during the swing, and we have our conservation of momentum during the collision. The only thing that we know at this point is the two masses of the bullet and the block. And after we get this little experiment set up and we fire the bullet into the block, we should be able to measure just how high the block swings. So maybe we have a lab assistant standing at some safe distance, watching and measuring how high this log swings up. And we'll say that that height is 15 centimeters, or 0.15 meters. That means I know the energy of the system at point 3, or location 3. I know that I have 0.03 kilograms for the mass of the bullet, 5 kilograms for the mass of the block. I know G and I know H, so I can find the energy in the system and I can relate it back to the energy at the beginning of the swing. However, if you didn't catch it yet, we've got the same amount of mass on each side of this expression, so we really don't even need to know it. We don't need to know the mass of the bullet and the block just yet. To get the velocity of the block after the collision, all I need is the height that the block achieves after the swing. So rearranging what we have there gives us square root of 2gh, and we'll go ahead and plug in the value of h, which was 0.15, times gravity times 2. We will square root that, and we get a velocity of 1.716. Now 1.716 meters per second, that doesn't sound very fast, but do keep in mind this is the velocity of the combined block and bullet after the bullet has become lodged inside the block. But this is actually slow enough that we can watch and we can measure the displacement of that block as it swings up. Well, now that we know what that velocity is, we can bring its value over to the conservation of momentum side. We have the mass of the bullet, the initial velocity of the bullet, which we're trying to solve for, the combined mass of the bullet and the block, times the velocity of the block after the collision, which we now know to be square root 2gh, or 1.716. I'm going to go ahead and drop the vector notation because we already know that we're maintaining the linear conservation. Before the collision, we're moving to the right, and just after the collision, we are moving to the right. And now is where the masses of the bullet and the block are actually going to come into play. Mass of the bullet was 0.03, mass of the block was 5, so over here we have 5.03 for the combined mass of the two, and then we're going to have to divide each side by the mass of the bullet so that we can get the velocity of the bullet. And this is going to come out to be 287.6 meters per second. And that is pretty fast. This is almost 3 football fields per second. And I'm just curious as to what the speed of sound going to be, that's 343 meters per second. So not quite a supersonic bullet, but it's getting close. And in case you're wondering, are there bullets that can exceed the speed of sound? Yes, there are. To do that would require a little bit of additional engineering into the system, but there are definitely forms of ammunition that can exceed the speed of sound. Hunters like those because that means that the shot gets to their target before the target can hear the sound of the gun going off. But there's also going to be ammunition that is much slower than the speed of sound. And a lot of that is going to have to do with how much powder is packed into the bullet. So the more powder that you can plug in, the more acceleration that you're going to get from the bullet itself. Another thing that we could do would be to change the mass of the bullet itself. We could make the mass of the bullet even smaller, and that would result in a faster exit velocity. But then you start messing with how much energy you can get within the bullet, because these two expressions, even though they look similar, they are not equal to one another. Momentum and kinetic energy are not the same things. Alright, I think now would probably be a good time to end this video. I'll think on it a little bit more. If I need to put in an additional example problem, I can. Otherwise, you can tune in during one of the office hour sessions or recitation sessions, and we can do some more problems with collisions and when it's best to use conservation of momentum versus conservation of energy. Otherwise, next video should be on chapter 10, and that will be the last chapter for the semester. So see you then.